Hi, my name is William Liu, and this is Dicanosa. We're security researchers for the Crusaders of Rust Security Research Group. Some of our previous work includes the entry bleed KSLR bypass or the message attacks. Over the past few months, we've been doing some Linux kernel vulnerability research. We achieved a few zero-day bounties and achieved many more CVEs. Today, we're coming here to share with you our favorite exploit, which we nicknamed an RbTree family drama. In this exploit, we compromised the Linux kernel through red-black tree transformations. Let us begin the fun. Just a quick agenda. We'll first talk about the subsystem we targeted, which is network scheduler or traffic controller. It's always important to understand your target before trying to exploit it. Then we'll talk about the star of the show, CVE 2025-38001. It's a zero-day we found, and to most people, it might look like a really innocuous bug, but we'll detail how we unleashed more capabilities from it later. Then Savi will talk about his RbTree attack against LTS and COS, and we'll conclude with a mitigations exploit. Just a disclaimer, there's going to be a lot of red flag tree diagrams, so brace yourselves. So why exactly should you guys care about our talk? Well, first, we compromised LTS, COS, and a mitigation instance of kernel CTF. Not shown in this picture is Ubuntu on ARM and Debian on x86. So with one exploit, it's cross-distro and cross-architecture. We made $82,000 from Google with this exploit. And we pulled off some shenanigans during the submission process that got the proof of work permanently removed from future bounty submissions. So we made a cultural impact on kernel CTF. Now let's do a quick overview on a Linux network scheduler. The whole point of this subsystem is to enable users to have fine-grained control over how packets enter and leave like the kernel network interfaces. Me and Savi actually found so many bugs in this subsystem that we effectively became unemployed Linux maintainers for the summer. One thing you always hear in this subsystem is the concept of a queue-disk. What exactly is a queue-disk, you may ask? Well, it stands for queuing discipline, and it represents the individual objects in the subsystem that controls how packets on-queue and dequeue from network interfaces. So the simplest queue disk, that's like the default for many interfaces, would be P50 fast. Aside from like a queue length that you could specify, the behavior is really simple. It's just like a queue. Packet in, packet out. Nothing complex here. The first queue disk with some behavior that will actually be really important later on is TBF, which stands for token bucket filter. It's like P50 fast, except this time, when you want to dequeue a packet, there has to be a corresponding token in the bucket. And the user can specify the burst rate of the bucket with how many tokens it's pre-filled with, or the rate at which tokens are generated and fills the bucket with. The next one is netm. This is actually, the code base for this is actually pretty bad. We highlighted duplicate in red because that's really important for later on. But the whole point of this is to act as a network emulator. You can duplicate packets, lose packets, corrupt them, delay them, reorder, and specify like a certain rate, etc. Now, all these individual queue disks make pretty good like fine-grained control for how packets enter and leave. But in NetDev, you can also chain them together for more fine-tuned behavior. So in this case, you have a TBF parent with a netm child, or a netm parent and a netm child. And if you enable duplication on both of them, you actually get a network DOS that took us about 2 months to fix. You could actually construct whole queue disk trees, and this enables really fine-tuned behavior with really complex interactions. But this comes at a cost with this level of abstraction because a lot of the queue disks are developed separately, and there's different assumptions and invariants that the developers assume. If you violate some of them, you'll get a bug. The star of today's show is going to be the hierarchical fair service curve, or HFSC for short. The algorithm of how it actually works doesn't matter at all, but it does support multiple children. And one last thing before we go any further. The queue disk, each of them has a handle. There's a major : minor number handle. The minor handle is always 0 for the root queue disk, but for child queue disks, like in this case, they're all non-zero. And that'll come later in the exploit when we show some of the code. So let's take a look at some of the historical vulnerabilities that the NextGet system has had. These are all snippets from the mailing list. Oh, the first one, there's discrepancy between the parent and the FQ caudal QDisk, and it causes a use after free. Another one in this case, another use after free in the DRR QDisk. Oh, HFSC now, that's the one we're going to be targeting later. There's a bug there. Another use after free in HFSC. Here's one that we found. If you have a hierarchical token bucket as the parent, or HTB, chained with a NetM, chained with a black hole QDisk, you can crash the kernel. And then if you chain NetM and NetM together with duplication enabled on both, you can get a DOS, which we discussed earlier. Finally, a network maintainer speaks up. He complains about all these nonsensical complex setups that us quote-unquote pawners are creating, and he blames the bug hunting crowd for all these bugs that we're finding. So let's be pawners today, and let's try to exploit a CVE, and let's dive right into it. For context, I was working on a research mode of syscaller for my master's thesis at the Massachusetts Institute of Technology, and I was talking to Savino. I was like, what should we fuzz? And during this time, there was a lot of network scheduler bugs, so we decided to target that. After a few days, my custom fuzzer came across this crash, which was a network soft lockup in the kernel, which means that the kernel has been stuck in a specific thread without a context switch for 20 plus seconds, usually implying there's like a really long loop, or in this case, an infinite loop. Of course, sysrepro was broken, so we had to manually reproduce and minimize it, and we ended up with these two programs. The two QDisks that are here are the HFSC and the NetM QDisks. So these were two of the buggier QDisks from earlier. We have buggy QDisk 1, combined with buggy QDisk 2, we get a new bug. Traffic control commands aren't really easy to write, so we had ChatGPT simplify us, give us some traffic control commands. And if you run this on the kernel, it would cause an infinite loop. What exactly is the root cause for this? Well, the traffic control commands earlier showed this setup. You have an HFSC parent with a NetM child with duplication enabled. Remember what I said about duplication being really buggy and important to note. Let's walk through some code. When your packet first enters HFSC on queue, it gets classified for the correct child. In this case, there's only one child, so it's really trivial. And then we have this first variable that gets set. This is really important. It's set to true when there's no packets previously in here. So this is really important. Then we call QDisk on queue on the child, which is NetM. And it goes here, because NetM duplication is enabled, we clone the packet, and we go to this really messy part of the code base that basically what it does is it globally disables duplication for this current NetM object, re-on-queues the packet back to the root of the QDisk tree, which is HFSC, and then after that finishes, it restores the original duplication value and then returns back to the caller. So now the packet goes all the way back to the root. It enters HFSC on queue again. Let's call this like the second level of recursion. And in here, the classification is trivial, and first is also set to true because there aren't any packets inserted yet. And this second level, it then calls on queue on the child again. Because duplication is disabled now in the NetM, the packet goes through. Then NetM return, the second NetM call returns. And then we go back to the second HFSC on queue call. Remember, first was true earlier, and we call this an init function. An init basically constructs the L tree, which is like the eligible tree of classes that are eligible to dequeue from. And it inserts the NetM object into this tree. So right now, this tree has the NetM object. Then we return back to the first level of NetM on queue call, and then that returns back to the HFSC call, the original HFSC call, where we call init again. Remember that first was also true in this initial case. And because first is true, this class gets inserted twice into the L tree. Now, when you do L tree insertion, it links the left node in. So now the object's left node points back to itself. So when the kernel tries to immediately dequeue the packet, it calls this L-tree get mine L function. And it goes from least to greatest. It tries to search for the correct class. This RbTree RB first function goes down the left node. Remember that the left node always points to the object itself. So the kernel just keeps looping down itself, and it creates an infinite loop. But it's an infinite loop. We don't really care. it's a DOS bug, it's not useful. We want something more. And the question becomes, can we unleash a more severe bug? The answer is yes, because Savino actually encountered a similar case a few months ago. The idea is to basically use a TBF to block the DQ, and then from there, if you block the DQ, you can then trigger use after free. You can check out more in this article later. So in the TBF case, you can minimize the tokens to block DQ. When TBF doesn't have enough tokens, the TBF gets rescheduled by a watchdog, so it blocks the DQ case. So if you set up TBF as the root, and you force a very low rate, you can then set up the HFSC and NetM duplication case to trigger the double insertion bug. But then DQ wouldn't be able to trigger because TBF doesn't have enough tokens, so it goes back to user space. We can then free the class with a traffic control command, and then we can trigger use after free by any activity on the L tree. Because when you free the class, this is what the L tree looks like. It's two of the objects that points to itself, and one of them gets freed, and one of them remains in the tree, so it looks like a very bad state in the kernel. In this case, if we trigger any network activity, we cause a KSAN and use after free, and now we can begin to pwn the kernel. I'll hand it off to Savino now to talk about the RbTree manipulations.
So the exploit we're going to present in the next few slides, is a data attack based on RbTree transformations. We basically use the Linux kernel RbTree implementation to cause a pointer duplication, and then we turn that into page use after free. So the attack is portable, and it works out of the box on multiple Linux distributions and on all kernel CTF baseline targets. And it's also very stable. It actually never failed on the kernel CTF instances. So we also received the stability bonus, just $10,000 bonus. Now, unlike this man, I want to confess that I don't wake up in the morning thinking how to weaponize the Linux kernel RbTree implementation. The only reason why I started looking into this is because when I converted the infinite loop into use after free, Kazan, as you can see from the Kazan's plot, it indicates the kernel is trying to access a node that has already been freed. So at that point, I asked myself, OK, maybe if I can take control over this node, I can do something interesting with it. Of course, the answer is yes. You can pawn all the current CTF instances. But let's do a step back for now. First of all, what is an RbTree? RbTree is a self-balancing binary search trees that uses color rules to keep itself approximately balanced. And the interesting part is that when a node is inserted or removed, this might cause a color violation. And the tree, in that case, will need to rebalance itself to restore the red-black properties. And this is very interesting, because if you look at the Linux implementation, the kernel uses this structure here, RbNode, to represent a node in the tree. Of course, the tree is just a bunch of these nodes linked together. And if we take control over this node, we can actually trigger transformation and achieve multiple interesting primitives, including a pointer copy primitive. So for this attack, we have two main components. The first, of course, are RbTrees. I think you guessed it. And the second component are page vector. So as you can see, RbNode is composed by 3 pointers. The first is a target pointer. It stores 2 pieces of information. The first is the address of the parent node, and then it stores the color information about the current node. 1 for black, 0 for red. Then we have 2 children, right child at offset 8, left child at offset 16. The second component are page vector, and as the name implies, this is just a vector of pages, of course. So we can allocate this by creating packet sockets, and then using setSockOp to allocate a packet ring. So what is a packet ring? Packet ring is just a ring buffer that can be shared between the kernel and user space, and is generally used for like asynchronous packet transmission or reception. But we don't really care here because we are using to pound the kernel. So when this function is called, we control 2 important parameters, because we can control the number of pages in the vector. So we also control the vector size, the object size, and we also control the page order. Another important thing is that pages are allocated using getFreePages, and this function returns the virtual address of the page. So when I say page, I refer to the page virtual address. So when a packet socket is closed, this function is called. As you can see, it frees each page, and then it releases the vector itself. And finally, we have packet and map. And as you can see here, it just iterates through the page vector and maps each page to user space using VM insert page. This function is very important. So just a quick recap, we control the number of pages in the vector, we control the page order, and we can map all the pages to user space. Now, the idea is this. We just want to trigger the vulnerability, insert the class twice into the eligible tree, then we free the HFSC class object, and we replace it with a page vector. Now, all the fields in the object are replaced by pointers to user-controlled pages. So we take full control over the node, because now the kernel treats all the pointers in the node, all the pages as RB nodes. So this was my first attempt, and spoiler, it failed. So first, we insert the class twice into the eligible tree, then we free the class, we replace it with a page vector. And what I try to do, I won't show this transformation here, but I just try to trigger a tree transformation to overwrite one of the pointers in the page vector with an RB node pointer. So my idea was just, OK, now I can just call packet and map and remap the node to user space and get arbitrary read and write in the kernel heap. The strategy failed because if you look into the packet and map implementation, as you can see here, it uses this very beautiful function called validate page before insert. And if the page is a slab page, then the function fails. And if the function fails, the strategy fails. And this was me when it failed. So then I tried again, and this time it worked. So the first part is identical. We just want to insert the class twice into the eligible tree. Then we replace the object with a page vector, but now we want to do something different. We insert a new class into the tree, a new node into the tree. And remember, the kernel now is treating our pages as RB nodes. So with this primitive, we can just write a pointer right into one of the controlled pages and leak the pointer to user space. Now, we want to use this information to forge and infiltrate a malicious node into the tree. We will call it Evil Grandpa. You're going to see why. And then we want to trigger 2 more kernel tree transformations to copy a page pointer from a page vector to another. OK, now, if you look at the exploit source code, all this looks very, very easy, because we only need to insert a new node into the tree, forge and infiltrate a malicious node, and then we only need 2 transformations to actually trigger the pointer copy primitive. The problem is that to understand why it works, we need to look into the kernel RbTree implementation. And this is a bit complicated. So let's just do a step back and let's analyze the exploit. So in the very first part, this is what I used to convert the infinite loop into a user after free. We just want to set up TBF with a very low rate. As you can see here, I just set it to 1, just minimize it. And then we send 2 packets to the interface. Now, from this moment on, the interface is completely unable to dequeue packets, so we can bypass the infinite loop. Now, we want to saturate Kmalloc 1K slabs, because we want new allocation to end up in a brand new slab. And then we want to set up the vulnerable class, of course. Now, we want to allocate a second class, and this time we want this object surrounded by page vector in the slab. This is very easy to do. We just need to allocate 16 page vector, then we allocate the object, in this case class 2, and then we allocate another 16 page vector. And as you can see now, the situation in memory, you can see on the right the memory layout, where we have the class surrounded by page vectors. Now we can trigger the vulnerability. We just need to send a packet to class 1. This is inserted twice into the eligible tree, but we don't trigger the infinite loop because the queue is blocked, of course. So now we can interact with the tree, free the object, and replace it with a page vector. As you can see on the right, we just replaced all the pointers in the RB node with user-controlled pages. So we just got rid of the old family, basically replaced all the family members with pages. Another important thing is that we want to the first squad word to 1. And if you don't do this, the kernel will crash. And I will show you why later. So yeah, GDB, sorry. This is the first, this is what we can see in GDB, basically. This should be a HFSC class object, but we replace it with a page vector. And if we inspect the eligible node address, we can clearly see all the pointers are now replaced by user-controlled pages. OK, now we can actually perform the attack. We just send a packet to class 2. Remember, this class in memory is surrounded by page vectors. Now the kernel calls this function here, RbTree insert, and prepares to insert the node into the tree. Now the kernel has to determine where to insert the node, and it does this by comparing the CLA field of each node with the CLA field of the class that is being inserted. Now remember, we replace class 1 with a page vector, so the CLA field is a very large value, so it takes the left path. Now we are inside one of the controlled pages, and remember, this page is completely zeroed out except the first quad word. We set it to 1. So now the kernel inserts the node, and it becomes the page right child. And now the kernel calls this function here, RbInsertColor. This function, we actually detect possible color violation and eventually trigger the tree will eventually rebalance itself. OK, this is a bit the tricky part. So you know that things change based on the perspective of the observer, right? So what we have on the left is the tree if we look at the tree from the class 1 perspective. Class 1 is the root node. As you can see, we have page P, it's the left child, and then we have the page P's right child, a class 2. We just inserted this node. But if you look at the tree from the page P's perspective, the tree is different. Because remember, RB link node never modified the page P parent. It's still set to 1. Why do we care about this? Because when RB insert is called, there is this check. And if the parent is a black node, and 1 means black node, the loop just breaks here. And the function returns we return to user place. So we just managed to leak a pointer, because the pointer was written into a controlled page. Now we want to forge and infiltrate a new node. First of all, we iterate for all the page vectors and locate the pointer. Now, remember that class 2 is surrounded by page vectors in memory, right? We want to place the malicious node right, yeah, it's called evil grandpa, as you can see here, 16 bytes before the next page vector in memory. This way, if we cast this address as a RB node, its left child will correspond to the first page in the target page vector. And the idea is that we want to overwrite this page with the address of page P. As you can see, now the family changed. We just infiltrated evil grandpa. And this is confirmed in GDB. As you can see, the malicious node is pointing 16 bytes before a page vector, and its left child is the first page. OK, now we need to trigger the first tree update. So we send a netlink message to the class 2. This will trigger the update, as you can see here. Update just removes and inserts the same class again into the tree. Very easy. So first part is removed. So we have RbTree removed. RB arrays augmented, and now the kernel prepares to actually remove the class 2. This is very easy to do because this class doesn't have children, so it just removed by zeroing out the page P's right child, like this. Now the kernel the same class is inserted again, and this part is identical to what we have seen before. So it takes the right path, node is inserted, but now something has changed. Because if you look at the tree from the class 1 perspective, the tree is always the same. But if we look at the tree from the page P's perspective, we just modify its parent. Now it's evil grandpa. And the last bit is 0. And this means this is considered a red node. So unfortunately for us, the tree now has to rebalance itself. So, and this branch here, of course, is not taken because the node is considered a red node. So first of all, page P is moved down the tree and becomes class 2 left child. Then evil grandpa is moved down, and we end up in this super messy situation because now grandpa has become the child of his grandchild. As you can see, the kid is like, grandpa, what is going on? So we also set the first page, as you can see here, in the target page vector, has been set to 0. And I really like to confirm things in GDB, as you can see. Now, this is the last step. We just want to remove class 2 from the tree. Now, if we remove class 2, first of all, evil grandpa becomes the designated successor node. And then the pointer is copied. We just trigger the pointer copy primitive because page B address is copied and becomes evil grandpa's left child, as you can see. So now we have a very powerful primitive because we just cause a page pointer duplication. As you can see here, the page B address is actually now in 2 different page vectors, in the original page vector and in the target page vector. So first of all, we need to locate this page. We just map all the page vector to user space until we find something. As you can see here, I'm using memchar2 and FF. So now we just created a mismatch between the page ref count and the actual places where the page is referenced, because the ref count is 3, like the page is referenced in the original page vector and mapped twice to user space, but we also copied the pointer into another page vector. This is very easy to exploit. We only need to unmap the page from user space. As you can see, the counter goes to 1. Then we close the first packet socket, and this will free the first page vector. Then we reclaim the page by writing 2 pre-allocated pipes. And as you can see in pipe right in the kernel, we have this very nice function here, alloc page. So the page is basically reclaimed. And finally, we close the second page vector. And this will cause the actual page use after free. OK, now, at this point, there are many ways to exploit a page use after free. Yeah. And you can use multiple techniques like dirty page table and so on. But there is a very nice trick that I like to use with a Linux kernel. And yeah, you've probably seen this. I just wanted to add that this up. It's signal FD. Basically, this is a very known technique. I only like to use a variation of this. And this enables signal entering through a file descriptor. As you can see, the user can provide 2 arguments. We don't care about the flags. If the provided file descriptor is -1, you can allocate a file, and the mask is stored into the pre data field. Otherwise, you can update an existing mask. And of course, if you can control the file structure, this gives you an U64 value arbitrary write primitive, basically. So what I like to do if I can get control over this file structure is just to swap the pre data field with the fcred field, which is a pointer to the current process credentials. And then I use multiple writes to set the credential to 0. Now, the problem is that we cannot control the lower bytes of the mask. And this is very annoying. Yeah. But there's a trick. We can just use the upper bytes to set the credential to 0. And we just need to start writing backwards. And as you can see here, we can just become root like this. So this exploit works out of the box on multiple Linux distributions on all current CTF instances. But I think I talked too much, and now it's time to demonstrate this exploit in live. So we created this very nice slide. We call this panel drink. So now if the exploit fails, we take a shot. But not here. We're very professional. We'll take the shot after. So now I don't know how to use computer. Please help me.
All right, so yeah, so we're not going to take shots here, but after the talk, we will give you guys one if it fails. So let's first target, let's say, the LTS instance. As pawners, that's what they call us, we like to get a reverse shell. So let's get ourselves, we're using a deprecated kernel CTF instance because this was like 3 months ago, but OK, everything's ready. You guys ready? 3, 2, 1. Oh, OK, so it worked there. Who are we? We're root. We got the flag. We got more demos coming up, so let's do the cost instance. Again, if I fail, I owe you guys a drink afterwards. We're going to go for reverse shell again. We're doing this because we really believe in the stability of our exploit set over here. And then, ready, go. Oh, another shell. That's the container-optimized version of Google's kernel CTF. So again, we're root, and we can get the flag. All right, this is wonderful. So let's get back to the talk. One thing, that's a brief aside. So during the LTS and COS submission process, when we submitted this, kernel CTF allowed unprivileged namespaces. So people had a lot of submissions going in. And part of the way they used to rate limit bounties was by only accepting the first submission every 2 weeks, regardless of whether it's a 0-day or an end day. And they even out the playing field by enforcing a proof of work, which lasted around 5 seconds. Now, us over here at the Crusaders of Rust, we really like to win, so we wanted to make sure we achieved the bounty. So we looked into breaking the proof of work. They basically implemented a sloth VDF proof of work system, and the modulus they used actually allowed for a lot of simplifications that cut it around from 5 seconds to 3-ish seconds. But we wanted to get it even faster. You can read more about it in our teammates blog here at Timothy Hirchin's blog. But we basically really optimized multiplication with Zen 5's AVX512 IFMA extensions and got the proof of work solver down to 0.2 to 0.4 seconds. Along with some other optimizations in like the Google form submission and et cetera, we got the total submission time down to 3.6 seconds, record time for kernel CTF. And because of us, they removed that proof of work component from future bounty submissions. So you guys can thank us for that. Now, so we killed LTS and we killed COS. Who's next? Knock, knock, mitigation, you're up. Let's look at what mitigations Google decided to bring upon us. The first one up the list is a k-malloc split var size. Basically, when you allocate objects, they want to separate objects that are of a known compile time size from a runtime determined size. So usually when you allocate an object, if it's of a certain size, it goes into a specific slab, let's call it k-malloc x. But now, if it's of a constant size, it goes to k-malloc x. And if it's of a non-constant size determined at runtime, it goes to din k-malloc x. Which is bad for us because HFSC class goes to k-malloc x, but PGV is of a runtime size, so it goes to din k-malloc x. But we're all kernel pwners here, or at least some of us are, so can't we just cross-cache attack this? The idea is to just basically have the slab allocator free one of the slabs, it gets returned to the buddy allocator, and then another slab needs a new slab, so it pulls from the buddy allocator and gets the page reused there. We can just do that again, right? Well, Google decides to bring slab virtual. I like to call it the pwnpocalypse, and this isn't very good for us. So you can fix cross-cache attacks by just making sure the slab allocator never frees the page back to the buddy allocator. But that's not very practical. You're going to run out of memory like that. Instead, they took an idea from partition alloc in Chrome, where each new slab is guaranteed to have a new virtual memory. So you can still free slabs back to the buddy allocator, but when another slab takes that page back again for making a new slab, it's guaranteed to have a new virtual address. So, well, doesn't this mean because pages are still being reused, we can't do pointer-style cross-cache, but can't we still have like a data-only based cross-cache? Unfortunately, when you look at the patch they proposed, they zero out the pages every time they get a new slab. So let's have a moment of silence here for the cross-cache attack. We can't use PGV anymore. The last mitigation I want to talk about, which is random k-malloc caches. Huawei actually upstreamed this to the Linux kernel starting around 6.6, I think. Basically, each slab has 16 random copies of itself. When you call k-malloc now, they take the return address. Remember, k-malloc is n-lined in this case, and using a per-boot random seed to determine which of the random slabs it lands into. So normally, you could bypass this with cross-cache, but remember, slab virtual prevents us from doing cross-cache. Thankfully, we identified a shared allocation code path among all the QDisk classes. When you call tctl tclass, which is, you can trigger to some user space, it calls the change function pointer. You can see it from this assembly. And for example, HFSC change class and HTTP change class both calls k-malloc on a class, but they share the same return address. So just a quick recap. K-malloc split var size kills the page vector. Slab virtual prevents the cross-cache attack for us to get page vector back. But random k-malloc caches provides us a limited type confusion opportunity because objects of the same slab size and the same allocation site will land in the same slab. So let's try to pwn mitigations now. Our initial attempt, we identified the HFSC class and the HTTP class of landing in the same slab. They have the same allocation site, so they'll bypass random k-malloc caches. Two fields that we can type confuse is the QDisk and the bstats field. Specifically, the packet offset in the bstats struct. This packet gets incremented from 0 when you start sending packets in the HTTP class. So we can forge a kernel pointer with 18 quintillion packets. We can't exactly send that. Time exists, and kernel CTF wouldn't allow that long of a submission either. All right, back to the drawing board, attempt number 2. What other fields can we target and overlap and type confuse? Well, we can bring back our good friend, the RB node, and also this time the xstats field, specifically the lens and borrows field, which is user readable, and you can also increment it as you send packets. So the idea now is to construct the same LTree construction with the vulnerable HFSC class, cause a use after free, replace it and type confuse it with an HTTP class, trigger a tree update through a series of tree transformations that Savi will cover to write the RB node into the HTTP class. And then we can dump the class's xstats to leak the RB left pointer, and then send packets to increment the RB left pointer and achieve a similar attack vector as you saw earlier. I'll hand it off to Savi now to finish it off with RbTree transformations.
Sorry. So basically, what I wanted to demonstrate with this exploit is that even partial control over our RB node can be enough to compromise the kernel, even with all the experimental mitigation in place. So first of all, we need to take control over an HTTP class. Now for this, we want to allocate 4 nodes. We allocate node 2, 3, 4, and then the vulnerable class, as you can see here, is inserted twice into the tree. Now we free the class, and we replace it this time with an HTTP class. So now we just created a sort of RB node type confusion, because of course the RB class is not supposed to get reachable into the HFSC eligible tree. So now we just want to delete class 4, and as you can see, the HTTP class is moved up and becomes class 3 right child. Now we delete class 2. We want to trigger a tree transformation now, and the class is inserted again on the right side. So now the tree is completely unbalanced on the right side, as you can see. So the class 3 is moved down, and now we just achieved the configuration we wanted because we just managed to overwrite the HTTP xstats with a node pointer. Now, first of all, we can lick this pointer. We only need to send a netlink message to the kernel, and the kernel will actually send us the extended statistics and the pointer. Then we can indirectly increment this pointer, because the lower bytes of the pointer overlaps with the extended statistics, the length variable. And this variable here is incremented by 1 for each packet processed by the HTTP class. So we just start sending packets to the HTTP class, and we can actually increment the pointer like this. And we want to make this pointer point 8 bytes before a controlled quad word. So we can just modify that and fake a new pointer. So we just created 3 layers of fake pointers, basically. Now, this pointer here is pointing 16 bytes before the target address, and this is the HTTP QDisk pointer. And the idea is that we want to trigger a transformation to overwrite the HTTP QDisk with the incremented pointer. And this is going to be hard to explain. Now, the idea is that if we manage to overwrite the HTTP QDisk pointer with the incremented pointer, then we can use the controlled quad word to fake a dequeue function pointer. But here we have a problem, because we cannot control the first quad word, which is the enqueue function pointer. So we need to find a workaround, and I managed to create a sort of delayed trigger, because we want to enqueue packets before corrupting the pointer. So the idea is that we set up TBF again, this time with we set the rate to 100, and then we send packets. This will be with the queue in about 5 seconds. So now we have 5 seconds to perform the attack. So now first we delete class 5, delete class 2. As you can see now the tree is completely unbalanced on the left side. So the HTTP class is moved down and becomes the controlled quad word right child. Pretty weird stuff. So now we just need to add 3 more classes to the tree. We add class 6, 7, and 8, and the magic happens. We just managed to overwrite the QDisk pointer with the incremented pointer. Now, if you are curious about this, just read the full write-up on the Google Security Research repository, because it's very hard to explain. You have to read a lot of source codes for this. But now we can actually fake the dequeue function pointer. And we just do relax and wait for packets to dequeue. And this we actually execute a RbTree gadget, a cop gadget. And now we can stack pivot into CPU entry area where we place our payload. There is a problem. The CPU entry area address now is randomized after kernel 6.6, I guess. Yeah. So does this mean I just blast you with more RbTree transformations for nothing? No. We can use the William prefetch side channel implementation to prefetch the SIA address. And this can be done with a very high accuracy, and it can also be used to bypass KSLR. It's basically entry bit, but without the syscall in the middle. So that's why we found all the targets. And now we also want to demonstrate the mitigation exploit live. And of course, we have another pound on drink now. And this has a 80% stability, so we are probably going to drink now.
We'll see, we'll see. It's time for the live demo. All right. In this case, if we get a reverse shell, the exploit's really not stable. So as CTFers, we're just going to dump the flag. We don't care. All right, you guys ready? Let's see if this works. It's prefetching now. Now it's a delayed trigger. Oh, I think it's usually pretty good here, so we'll see. Oh, we got the flag. Okay. Well, I guess we won't be taking shots because of failed exploits, but we can still drink with some of you guys afterwards. The kernel crashed afterwards, but that's okay. So that's the end of our talk. Before we finish up, I'd like to acknowledge a few people. First of all, I'd like to acknowledge Professor Manjayan of the MIT Matcha Group and MIT CSAIL for funding my fuzzing research project. We wouldn't have found the bug otherwise. And I would also like to thank my teammates for helping us with the submission process. So Larry Yuan of Cure53, Timothy Hirchin of AOPS, he's the performance optimization genius, and Bryce Kasahe of Zelic. Without them, we wouldn't have won the LTS and cost submission, and we might not even have this talk today. But yeah, thank you very much for listening to our talk. We somehow managed to get through 327 slides, but feel free to contact us at savi@systemfailure.io or me at will@willroots.io. And you can also contact the Crusaders of Rust and come play our CTF next year. Thank you so much for listening, everybody.